right, we are going to start off here this morning with vocabulary, pick up where we left off yesterday. I believe the last word I gave you guys yesterday was ionic bond. Yeah, should be right. And so we're going to pick up here today with a covalent bond. Try to get all the vocabulary into you today here, so you have lots of time to study all these 20 words. Covalent bond is a bond that results from atoms sharing electrons. Sharing of electrons. As always, guys, if I get going too fast, you can either slow me down, or also don't forget, if you feel like you need this, don't forget that I posted that resource folder that has these vocab words in it that you can always look up if I go too fast and you miss a couple of words or something like that, okay? So covalent bond is formed when two atoms share electrons. We talked a little bit about a hydrogen bond yesterday. And remember that a hydrogen bond is really not a bond, but it's just an intermolecular force of attraction. And it occurs between hydrogen atom that's on one molecule, and then it goes to an unshared pair of electrons on a different molecule. All right, hydrogen bond. The next word is intermolecular force. And of course, I threw this in there just to make sure that you understood what an intermolecular force was, since it was in the definition of hydrogen bond. And it's just an attractive force that occurs between any two molecules. Inter, again, is the prefix that means between. So it's a force between molecules, intermolecular force. Our next word for today is compound. We're going to study two different types of compounds, ionic compounds and molecular compounds. But in order for us to be talking about a compound, there has to be at least two different types of elements bonded together. And they have to be in a fixed proportion. When I say a fixed proportion, what I mean by that is if you think about, for example, you guys all probably know the formula for water, chemical formula, H2O. And so the proportion is that there are two hydrogens for every one oxygen, right? H2O. If I change that proportion, I no longer have water. And so, for example, H2O2 is a substance that most of you are probably familiar with. It's in a brown bottle in your medicine cabinet at home. Hydrogen peroxide, H2O2. And if you've ever had hydrogen peroxide used on you, you know that water and hydrogen peroxide behave differently. If I have a cut and I pour hydrogen peroxide on it, it's going to bubble up. As that hydrogen peroxide decomposes, undergoes a chemical reaction, produces that oxygen gas. If I pour water on my hand, nothing happens. So fixed proportion means that the chemical formula is always the same. Water is always H2O. Okay, an element. An element is only made of one kind of atom. So again, we know, for example, water cannot be an element because it has hydrogen and oxygen in it, H2O. So that's clearly not an element since there's two different kinds of atoms there, hydrogen atoms and oxygen atoms. Okay, this word is pronounced cation. Cation. That's why I put a picture of my kitty in here to help you guys remember the pronunciation of it. A cation is an atom or group of atoms with a positive charge. I'm going to even do this. What do you think of that? Positive? Get it? Cat, positive charge. Who's laughing at home right now? Thanks, Livia. Just trying to help you guys remember these words. Anything I can do to help stick them in your brain, it's a good thing, right? So there's my big old cat, Callie. 18 pounds. She's a monster. All right. So anions are negatively charged. Okay? Atom or group of atoms with a negative charge. Anions are negative ions. Hey, Scott. Anions are negative ions. Anions, negative ions, negative charges. Okay. All right, here's a big old monster chemistry word, electronegativity. Electronegativity. This word is really an important word. It's an important idea in chemistry because this is kind of what we understand that dictates whether something is going to give and take electrons or whether they're going to share electrons. So it's an atom's ability to attract electrons from the other atoms that it's bonding to in a compound. If one atom has a much, much larger electronegativity than the other atom that it's bonding to, it can take the electrons. So then we form an ionic bond. And if the electronegativities of the two atoms are relatively similar, then the two atoms will just share electrons and we'll have a covalent bond. And based on what I talked about with you guys yesterday when I lectured, of course, ionic compounds have very different properties from molecular compounds. So the way the electrons behave plays a big role in the properties. And of course, that's what we're going to be studying. We're going to be looking a lot at the properties of these different substances. Proteins, carbohydrates, lipids, water. Okay. So how strongly an atom attracts electrons is an important idea in determining the behavior of not only that atom, but whatever compound that atom is in. Okay. So as I just kind of mentioned here, we've got ionic compounds. Those things are made up from cations and anions. In other words, elements have transferred electrons. One atom gave, one atom took. And then as they became these ions, they're attracted to each other because of their opposite charges. That's an ionic bond. And we call those substances ionic compounds. Ordinary table salt is probably the most common example of an ionic compound. You guys would all be familiar with ordinary table salt. White crystalline solid, readily dissolves in water, has a very, very high melting point. You would not be able to melt table salt on your stove. In contrast to that, we have molecular compounds. Of course, the definition is that they're composed of molecules, but since we just talked about molecules, we understand that that means there's covalent bonds between the atoms. So atoms are sharing electrons. Of course, elements, as they share electrons, again, it's because their electronegativities are relatively close together. One atom is not strong enough to pull the electrons off of the other atom, so they share. Then they form these molecules, and then depending upon lots of things that are going on with the molecule, including the types of bonds, whether they're non-polar covalent, polar covalent, single, double, triple bond, lots of stuff there that we haven't talked about yet. But depending upon the type of bond, types of atoms, and the shape of the molecules, you're going to get different kinds of intermolecular forces. And it's those intermolecular forces that really dictate whether or not the substances have high or low melting and boiling points and things like that. So there's all kinds of crazy chemistry going on when we start thinking about molecular compounds. But ordinary table sugar is an everyday example of a molecular compound. Sugar. All right, that is our last vocabulary word for this unit. Okay. So close out of there. Let's see. Got to figure out where I'm trying to go here. Here we go. This is what I want to do. All right. We are going to look at this atom builder simulation today. We're going to learn about how atoms work. We're going to learn about protons, neutrons, and electrons, where they go in the atom, how they fit together, how do they behave when we put them together when they're by themselves, okay? And so I'm going to highly recommend that you guys take some notes while I'm doing this simulation with you. And Ms. Hall is probably going to be very, very kind and type into the chat box kind of some of the key things that I'm pointing out. Amelia, this is not a lab. It's just a simulation that I'm going to use to lecture off of. And so again, you're going to want to kind of take notes, but there's not a handout or anything like that to go with this. Okay. But Ms. Hall, as she said there, she said yes, she's going to be typing stuff into the chat box. She did that in the previous classes this morning. So kind of keep an eye on the chat box, and Ms. Hall will kind of put in the key things, the most important things there to make sure that you guys are taking good notes, okay? So let me just kind of walk you through the picture here on the screen. Notice in the upper left-hand corner, protons, neutrons, and electrons. It's just going to be a place for us to kind of keep track of what's in the atom, because as we put lots and lots of protons, neutrons, and electrons in here, it's going to be a little bit harder to keep track of how many there are. So you'll be able to see that very clearly up here. You'll be able to count them easily. Okay, over in the upper right-hand corner, we've got a little tiny picture of the periodic table. Of course, it just has the symbol in it. We can't see any atomic numbers or anything like that, but it's going to help us to identify what element we're dealing with as we build the atom here using the protons, neutrons, and electrons. This deal down here with the net charge, is just going to help us to understand, again, the charges of the subatomic particles by themselves, and then it's going to ultimately tell us if there's a charge on our atom, which means that it's no longer an atom, but instead an ion. Okay? And then, of course, the little scale down here, the little balance, is going to help us to keep track of the mass number. I'm going to also click this other box here that says stable and unstable, and we're going to talk about it just a very, very little bit. I'm not going to focus on stability, nuclear stability, but that's what this is going to deal with, is nuclear stability. So let's go ahead and start by putting a proton into the atom. So I'm going to go ahead and just come up here and drop this proton in. Oh no, fell down. Well, maybe it goes here. Whoop, look at that. Drawn to the middle. Okay, so that kind of shows us where protons belong in the atom. I tried to put it out here in these rings, wouldn't let me, and put it down in here in the middle. Here's a vocabulary check for you guys. See how you're doing, see if you remember things. You guys, please type into the chat box, what do we call this middle region of the atom where protons hang out? What is that vocabulary word? Type it in. I want everybody to type it. Let me see you all participating in class today. The region where the protons can be found in an atom. What's that called down there in the middle? And here come my responses. I got a few of you typing in the chat box. Looking good, looking good. Way to go, kiddos. Yes, nice work. All right, yeah, that's the nucleus. So the nucleus is that central region of the atom. It's very, very dense. Remember we talked about that yesterday. Trying to squeeze every living person on the planet into my classroom. It's like how dense the nucleus is. It's incredibly small. Remember the little marble I showed you yesterday? Be like the size of a marble if the rest of the atom were a football stadium, an NFL football stadium. All right. So I want to point out up here in the upper left-hand corner, look, it shows us we've got one proton in the nucleus. Notice the word hydrogen popped up here when I put that proton in. So it says hydrogen. And then right up here above the blue dotted circles, we see positive ion. So right now we understand that this thing is an ion. And if we come over here to the periodic table, you can see H, hydrogen, is highlighted. And so that tells us what our element symbol is there, H, and it shows us the position on the periodic table. Look at that. And then down here, we've got a net charge of +1. So that gives us an indication of the charge of a proton. As I told you yesterday, the charge on a proton is +1. And then directly underneath that, we can see the mass number is 1. And I told you yesterday that protons had mass. Their mass was 1 AMU. And so that's what this mass number is showing us here, mass. So it has a positive charge, and it has a mass of 1. So we can kind of learn all that about that proton. Okay, so let me take that proton out of there. Put the neutron in. Where's the neutron go? Does it go out here in the blue circles? Nope. Puts it into the nucleus. All right, I don't want that to confuse you, so let me shut that off for just a second. So the neutron belongs in the nucleus. Notice there's one neutron up here in the upper left-hand box. My element symbol went away. There's no element symbol. Nothing on the periodic table is highlighted. The net charge here is 0. So the neutron has no mass. No charge. but it does have mass. Look down here in my mass section. The mass is 1. So it has the same relative mass as the proton. So neutrons and protons have the same relative mass. Okay? Again, when I say relative, I mean we're comparing the two, and really we're going to compare all three, protons, neutrons, and electrons. And the mass of the proton and the neutron are close enough to each other that we call them the same when we just are talking about the three particles, the relative masses. All right, let's go ahead and take that neutron out of there and see what happens when I put the electron in. Okay, well, everything else went on this orange dot, so let me put this electron on the orange dot. Ooh, went out to the blue circle. Okay, well, what if I try to put it on this outer blue circle? Nope. Apparently it has to go into that inner blue circle, doesn't it? Okay, notice one electron up here in our little box to keep track of. No element. Electron isn't contributing anything to the element symbol. Notice there's no name or anything here. But it does have a negative charge. So an electron's charge is negative. And take a look down here. Mass is 0. The mass of the electron is so much smaller than the mass of protons and neutrons, it's like it doesn't even matter. It's like like I told you yesterday, if I'm going to get onto the scale in the morning, see how much I weigh, if I notice that there's a little piece of fuzz on my shirt or something like that, I don't need to bother to take that piece of fuzz off. It's not going to affect my weight. Not on the scale anyways. Right. Well, I'm going to come back over here now. And I want you to notice the color of my proton and notice the color of this X. It's supposed to be kind of actually a hint, right? They're both orange. Notice the name is orange, and notice that the symbol highlighted up here on the periodic table is orange. Do you think those things have anything to do with each other? Is there a reason why all this is orange? I hope that you're thinking yes right now, because they are all very much connected. So notice that this says right here now, neutral atom. Neutral. What does that mean? Neutral. Well, if we look over here, it has no net charge. 0. Because we have one proton and one electron. And so if there's no net charge, that kind of tells us that the charges of protons and electrons must be equal and opposite. Right? A proton and an electron have an equal and opposite charge if there's no net charge when I have one of each. Also notice that there's now this little black box around here. So it's kind of showing that this is a pair, black box. And notice this word up here, neutral atom. It's black. Keep an eye on that. It's an important idea. Okay? And so again, our mass is 1 because we have that one proton there. Now this is a stable atom in terms of the nucleus. Okay, it has nuclear stability. What happens if I add a neutron? Now I have one of each particle there. Okay, one of each particle. So one proton, one neutron, one electron. There's no net charge because I have an equal number of plus and minuses. That means positive charges for protons, negative charges for electrons. Notice my mass number here is 2 because as we just learned, we have mass from both the proton and the neutron. Okay, both the proton and the neutron add mass to the nucleus, so my mass number is 2. Again, here we are on hydrogen. Now, I don't know if you guys noticed this before when I had just the electron in there. Notice, didn't say anything up here. Just the electron isn't considered an ion, isn't considered an atom or anything. I have that up there. It's a neutral atom. So what happens if I add another electron? Well, notice that it goes on that same inner circle. And now notice that I've got a negative ion. So when I had just the hydrogen atom a moment ago, I had a positive ion. It was orange. Go with my protons. Now, when I put 2 electrons in here, I have a negative ion. Notice the color, blue. They're both on that inner circle. And look over here at my net charge. I've got a proton and an electron that balance each other out. Then I've got this other electron over here all by itself. So there's an extra electron. So now I have a net charge, -1. So I have an anion here. Okay, negatively charged ion. So what would happen if I added a proton to this? Let's see. Oh, it becomes helium. Look at that. It changed elements. Went from here over to there. Changed elements. Hydrogen to helium. So 2 protons changes the element name. Comes over here on the periodic table. Changes the element symbol. And now notice the charge. Oh, Natalia, I see you raised your hand. Go ahead, dear. Natalia, you got a question? No net charge because we have 2 positives and 2 negatives, right? So 2 protons, 2 electrons. The charges are equal and opposite again. But notice that this is unstable. The nucleus is bouncing around in here. Let's talk about that for a second. So opposites attract. You guys have probably heard that before. Opposites attract. Well, what's the flip side of the coin? If opposites attract, things that are alike will repel, right? Like charges repel. And so I've got 2 protons in there in the nucleus. They're very, very close together. They're alike and tend to want to repel each other. That's what makes this nucleus unstable. It's going to want to undergo nuclear decay. But neutron kind of acts like the glue that holds the nucleus together. Once I put that neutron in there, it calms down, stable. And so there's something that happens here between protons and neutrons. There's an attraction between protons and neutrons, even though there's no charge on a neutron. Remember, notice my charge didn't change when I added that neutron in there. There's a different kind of attraction. Chemists call it the strong nuclear force. It's a very, very strong force of attraction between protons and neutrons over very close distances. And it's stronger than the repulsive charge of just the protons pushing against each other. So it kind of holds the nucleus together. So notice my mass number now is 3. Where does that 3 come from? Well, remember, it comes from the 2 protons and the 1 neutron. In fact, if I add another neutron, notice my mass number changes. I still have a stable atom. And the charge and stuff doesn't change because I haven't changed positive or negative stuff. I'm just adding neutrons that have no charge. They're neutral. Okay, well, what do you think is going to happen if I add another proton? unmute your microphone or type into the chat box. What do you think will happen if I add another proton? The atom's identity will change, says Audrey. Let's test that out. Look at that. The identity did change. Good job, Audrey. We now have lithium. Lithium has 3 protons. Look over here in the periodic table. I don't know if you've been noticing this, but hydrogen had 1 proton. That's the first element. Helium had 2 protons. That's the second element. Now lithium is the third element, has 3 protons. Almost like there's something going on there, right? All right, well, that's driving me nuts, that jumping around. I'm going to add another neutron to the nucleus to make that stable, so I don't have to keep watching that bounce up and down like that. I can't remember if I mentioned this to you guys or not, but if you haven't already done this, you might want to pull up under classwork and resources. Remember, I've got a periodic table down here for you guys, right? Might be a real good idea if you have a copy of that in front of you. I don't know if you can look at that on your screen at the same time you're looking at what I'm sharing on your screen. If not, you could always print this out. If you have capability of doing that, that might be a really, really good idea. But if you look on that periodic table, you will find what's called the atomic number. And the atomic number is what's changing as you read left to right and top to bottom in the periodic table. Hydrogen's atomic number 1, helium's atomic number 2, lithium's atomic number 3. And so that atomic number is linked to our protons. As Audrey correctly predicted, the identity of the element changes as I add protons. And so that atomic number and the identity are both linked to the number of protons. Okay? So notice I have an equal number of protons and neutrons, and this is stable. I had to add one in there to make it stable. What happens if I put an extra one in? I now have more neutrons than protons. Well, it's still stable. The nucleus is still okay. It's pleased to have an extra neutron. Notice we just changed the mass number. A moment ago, the mass number was 6. Now we're at 7. I wonder if I could add 2 neutrons. I wonder if it would still be okay if I put an extra neutron. Nope, doesn't like that. 1 extra neutron is enough. All right, take a look up here. Notice we have a charge. This is a lithium ion. It's positive, orange, right? Kind of goes back to our protons again. If you look at the net charge over here, you notice it's positive because there's 3 protons and only 2 electrons. So they've got that circle around here again to show you where the charge is balanced, but there's this extra plus sign out here. So we have a plus charge of a net charge of +1. Okay? Now, on a side note, it's kind of interesting that this is a stable atom in terms of the nucleus, but it's also a stable ion because this first energy level is full. Watch, notice when I try to put another electron in there, it won't let me put it on the first energy level. It goes right to the second. Okay, so the first energy level can only hold 2 electrons. That's kind of an important idea for chemists. Okay, and lithium is kind of happy to have a full energy level there and not have that extra electron. If I put that electron on there, we've got a neutral atom. So it has no net charge. Notice the positive and negatives over here balance out because we have equal numbers of protons, orange circles, and electrons, blue circles. But lithium tends to form this ion right here. That's where it's chemically stable. In a similar fashion, if I add another proton, I'm going to change this to a beryllium. I'm going to put another neutron in there to keep it from jumping around. Notice with lithium, we could have equal number of protons and neutrons, and it was fine. But with beryllium, I've got to have an extra one. Isn't that interesting? Now, notice our charge. It's the first time we've seen this. Net charge of +2, because there's 2 protons more than there are electrons, right? 4 protons in total, only 2 electrons gives me a net charge of +2. Can I put another neutron in here and keep it stable? Nope, doesn't like that. So there's only one really stable isotope of beryllium. That's interesting. Okay. All right, let's go ahead and add another proton, get the boron there. How many protons are in boron? 1, 2, 3, 4, 5. Look over here at the periodic table. Hydrogen is 1, helium is 2, lithium is 3, beryllium is 4, boron is 5. So our atomic number is 5. Again, equal to the number of protons. All right. Look at this charge. We're getting more and more positive in charge. So this boron ion +3 charge got a positive charge of 3 because of the 3 bonus protons that don't have partners here. But let's see what happens if I start adding some electrons. Okay, notice I can bring that charge down. And if I get enough electrons in there, oh, look at that. We're neutral again. Everybody's happy. Protons and electrons balance out. All right, I'm going to go ahead and add another proton, another neutron, and another electron to get us to carbon. Notice that we're just continuing to add electrons to this outer energy level. Okay. And carbon is an atom that tends to like to share electrons. So it's going to share electrons with other atoms to become stable. Now nitrogen, on the other hand, as we move to atomic number 7 here, element nitrogen. The second energy level, and I'm going to say this as a kind of a general statement, most atoms, most elements on the periodic table tend to want to have 8 valence electrons. Remember, that was one of our vocab words yesterday. Those are the electrons in the outermost energy level. So the exceptions to that are lithium, beryllium, boron, hydrogen, and helium. They tend to only want to have 2 electrons because that leaves their first energy level stable, and the atom can handle that. The atom can't handle having a ton of extra electrons without protons to be attracted to it. But when we get to nitrogen, all of a sudden things change. In order for nitrogen to be chemically stable, it tends to want to fill up this outer shell with electrons. So it tends to want to have 8 electrons in the outer energy level. And so when it does that, of course, it's going to form a negative ion, an anion, because now it's got a charge. It's got 3 electrons more than the number of protons. And you kind of see that readily up here as well. So this is the nitride ion. And again, it's chemically stable. It's electrically stable because of the fact that it's got a full outer energy level here. Let's look at the neutrons real quick. Oh, obviously it doesn't want me to take one. Can I add one? Yep, it's still okay if I have an extra. Can I add 2? Nope, doesn't like that. So nitrogen can either have an equal number of protons or an extra neutron. Either way, it's okay. Oxygen. Notice the charge went down. It's only +2 now because I've added a proton. This is a stable oxide ion. Got 8 electrons. It's happy. The nucleus is also stable because of the number of protons and neutrons in there. Can I take a neutron away? Nope, doesn't like that. Can I add a neutron? Yep, that's all right. So I can either have, 8 or 9 neutrons there. It's fine. When I go to fluorine, notice that fluorine doesn't like having an equal number of protons and neutrons. It wants an extra neutron. Can it have 2 extra neutrons? Nope, doesn't like 2 extra neutrons. One's enough. So fluorine has only one stable radioisotope. Okay. Notice again, I still have 1 extra electron than I do proton. So it's negatively charged. This is a negatively charged fluoride ion. And if I finally, and notice my mass number keeps changing as I add protons and neutrons here, right? As I round this out, add another proton, get to neon, notice my charge balances, got the big circle around all the pluses and minuses, nothing outside of the circle, so they're equal. No net charge, 0 for a number. My mass number is 20 because I have 10 protons and 10 neutrons. I could take all the electrons out of here and it wouldn't do anything to my mass. You see that? Oh, look at that. It won't even let me take an electron out of the first energy level. It replaces it. How about that? Okay, so as I add or subtract electrons, my mass doesn't change. It's only the protons and neutrons that change the mass. All right, and again, we can kind of test that by adding another neutron in there. Well, actually, let me take a neutron out. Can neon? Nope, doesn't like that. So can I have an extra neutron? Yep. Neon's good with an extra one. How about 2 extra ones? Can I add 2? Ooh, look at that. Neon can handle 2 extra neutrons. That's kind of interesting. Can it handle 3 extra neutrons? Nope, doesn't want 3. 2's enough. Notice the mass number over here keeps changing as I move neutrons around. As I move protons around, my mass number changes, right? All right. At this point, does anybody have any questions? Any questions? All right, I'm going to come down here at the bottom. I'm going to click on symbol. And we're going to look at this from a kind of a little bit of a different perspective. This is called the nuclear symbol. And this is what we use. This is kind of our shorthand in chemistry. Instead of writing everything out, we'll use nuclear symbol notation to talk about atoms and how many protons, neutrons, and electrons they have. So we're just going to kind of do the same thing. We're going to add a few protons and neutrons in here, and we're going to watch how these symbols change. What I want you to pick up on right away is notice there's the little mass thing over here, and there's the little charge thing right here. So let's see what happens when I start putting stuff in. Let's start with a proton again. Notice orange number down here in the lower right-hand corner is 1. If I take it out, it's 0. Of course, everything's 0 if I take it out. If I put it in, it's 1. The little 1 here next to the mass, that implies that that's my mass number. And the little +1 over here by the charge implies that I've got a +1 charge, again, because I have just the proton. It's not electrically neutral until I add that electron in there. So now notice my charge went to 0 because I have an equal number of protons and electrons. Notice my mass didn't change when I added that electron. Mass doesn't change. Now if I add a neutron, notice my mass changes. But this is the number of protons. That's why it's orange. That didn't change. And of course the charge didn't change because neutrons have no charge. I can add an extra electron in here because hydrogen tends to want to fill its energy level, so it wants 2 electrons. So notice now the charge is -1 because I have 2 electrons. Look up here in the corner, if you will, and only 1 proton. So my charges are unbalanced. Okay. Yeah, I'll post the video, Amelia. Welcome. Have a good afternoon. So I can put my my neutron in there, again, that changes the mass number. If I add another proton to it, look at that, changes the element symbol. We learned already that protons dictate what element we're dealing with. Notice my atomic number changed. I'm now on element 2, right? Hydrogen is 1, helium is 2. So the 2 oranges, atomic number 2 down here, that orange is my atomic number, the element number on the periodic table. Because protons and electrons are equal, there's no net charge. And again, notice that my mass is 3 because I have 2 protons plus 1 neutron in the nucleus. All the mass comes from whatever's in the nucleus. If I add another neutron to the nucleus, notice that that mass number changes, goes up to 4. However many particles are here, that's my mass. Can I add a 5th one? Look at that, changes my mass. Okay, let's add another proton. Notice it changes the identity of the element. I go to lithium. Right now we've got an ion, +1 charge because there's 3 protons. And we know by looking at this, if the charge is positive, that means there's an extra proton when I compare to electrons. So if there's 3 protons, there can only be 2 electrons if I have a +1 charge. And we can see that in the picture. All right, so if I want that charge to go to 0, I have to add an electron. Notice it goes to that second energy level again. All right, lithium's mass is 7. By adding another neutron, we add another proton. Notice the atomic number changes again. I go to a different element. My mass number changed when I added that proton. Positive charge again. What happens if I add an extra electron? Notice now that my charge up here in the right-hand corner is negative, and it's blue. Again, goes back to the electrons. Right now I've got more electrons than I have protons. Well, I can tell how many protons I have because that's my atomic number. That's the orange number down there in the lower left corner. So if I have 4 protons, that must mean I have 5 electrons because there's more electrons because my number's blue. Okay, it's negative. Remember, electrons have a negative charge, protons have a positive charge. So I have more negative charge, more electrons than protons. Go ahead and add another proton. Notice my charge goes to 0 because now they're equal. I have 5 of each. And boron has a charge of 10 usually. No, 11. Boron's charge, mass, boron's mass is 11, I think. That's it. I think that's stable. Yeah, that'll give me my stable isotope of boron. And again, as I keep adding protons, neutrons, and electrons here to my atom, that's going to change my protons, changes my atomic number. That's why it's orange here in this figure. Protons are orange, right? My mass is the sum of what's in the nucleus. So I just have to add up the protons and neutrons. Sum of what's in the nucleus is my mass number. And then my charge comes by comparing the protons and electrons. If they're equal, my charge will be 0. If I have more protons, my charge will be positive. If I have more electrons, my charge will be negative. Anybody have any questions at this point? Okay, notice I'm going to come down here to the bottom and I'm going to click on Game. This is where you guys need to participate. Again, I'm going to wait for you to type in responses into the chat box or unmute your microphone. Either way, I will accept both happily. Okay, as we play this game, I want you to tell me what to fill in. So I have to find the element. So as I look at all these little crazy symbols here, how do I know by looking at the periodic table what element this is? What element is this? Olivia says the number of protons. Okay, well, how many protons are in there, Olivia? 1. I concur, 1. So that means, what element am I looking at if there's one proton? What is the first element on the periodic table? Tierney, you are correct. It is hydrogen. Next time, answer with an exclamation point, not a question mark. Have some confidence. Good job. Okay, now look at this. When I clicked on hydrogen, notice what popped up down here. It says, is it a neutral atom or is it an ion? Is this going to be a neutral atom or an ion? And you can just put in there atom or ion in the chat box when you answer my question. Is it neutral atom or is it an ion? I want you guys to all participate in class. My expectation is that you're all going to type an answer in the chat box. All right, and Olivia and Natalia, Emmy, Grayson, everybody's saying ion. Okay, well, I'll click on ion, but I want to know how we know that. How do we know, Jacob? Good. How do we know that it's an ion? What's the clue? There's more electrons. Yes, Livia. I'll tell you what, Miss Hall, Livia needs an atta girl for the day. Are you with me?
Got it.
Thank you. Olivia, do you know what that means? You know what an atta girl means in my class? It means extra credit because you're rocking the answers today. Appreciate your participation. So Miss Hall's putting extra credit for you in Infinite Campus. Yeah. Thank you for participating. Appreciate it. All right, here's the next question. We got that one right. Did you guys see the smiley face there? I need to figure out what element this is. 7 protons, 8 neutrons, 7 electrons. What element is this? Audrey says nitrogen. How'd you know that, Audrey? What was the clue? Amount of protons. Very good, girl. Yep, that's right. So nitrogen is the 7th element. Look, 1, 2, 3, 4, 5, 6, 7. Nitrogen's atomic number 7. 7 protons. All right, is this a neutral atom or an ion? Atom or ion? Atom or ion? Oh, look at those responses. Yes, that's right, guys. Good job. It's a neutral atom. How do we know? Equal number of protons and electrons, right? Equal number of protons and electrons. Look at that smiley face. Good job. All right, so here's another one very similar to the one we just did. What element is this going to be? Jacob, oxygen. Is it going to be a neutral atom or an ion? All right, I got 2 ions there. Let's check it. Yeah, that's right. How do we know it was going to be an ion? Had an unequal number of protons and electrons, right? We got to look at protons and electrons to see if it's going to be an atom or an ion. If you have unequal number here, it will be an ion. Okay, what element is this? Okay, Audrey says hydrogen. And is this an atom or an ion? Atom or ion? Natalia is saying it's an atom. Let's check. Bingo. Has the same number of protons and electrons. Therefore, it's an atom. All right, last question. What's the element? Olivia, Jacob, nitrogen. Okay. Thank you, guys. And is this going to be an atom or an ion? Oh, look at that, man. I didn't even have the words out of my mouth, and Audrey is responding to my question. Nice work, girl. Hey, look at that. Good job. Yes, Jacob. Well done. Okay. Look at this. Nice work, team. We rocked this. I'm confident that there are several of you who know what you are doing based on that little game and your participation. I appreciate your participation in the game today. Thank you very much. All right. Last thing we're going to do here today real quick together is come over here to today's date under our classwork page. And you guys should be able to pull up this worksheet called Isotope Practice. Isotope Practice. Go ahead and pull that up. Okay, and again, you're going to have a periodic table in order to do this practice. I'm going to do just a couple of these with you, and then I'm going to let you guys fill in the rest on your own. So let's start here with the first one. Number one always seems like a good place to start. The symbol is C. We're going to have to find that on the periodic table. Locate C on the periodic table. Once you locate that, very first thing I'm going to recommend you do is tell me the atomic number, because that is right on the periodic table. What's the atomic number of the element C? Okay, I got a couple of responses in the chat box. Number 6. Uh-oh. Come on, 6. There we go. Number 6. All right. So we just read that right off the periodic table. The atomic number is 6. Now, once I know the atomic number, what else is that going to help me with? What did we determine today that the atomic number tells us? Protons. That's right. Good job, Audrey. Well done. So if I know the atomic number is 6, I also know that the number of protons is 6. Is there anything else that I can glean from knowing the atomic number and the number of protons? Take note. There's no charge next to my element symbol. If the symbol has no charge, what else do I automatically know? Hey, look at that, guys. Well done. Jacob, Audrey, Livia. Yes, the number of electrons is the same as the number of protons. If it doesn't have a charge, protons and electrons are equal. So I can go ahead and put that in. All right, so the last thing I have to fill in here is the number of neutrons. How do I get the number of neutrons? Oh man, Olivia's already got it in there. 7. Where'd you get 7 from, Olivia? The mass subtracted by the atomic number. That's right. That's perfect. Remember that protons plus neutrons give us the mass. Therefore, if I know the mass and I know the protons, I can subtract protons from the mass number, and that would give me the number of neutrons. So 7 plus 6 equals 13. That's my double check there. Perfect. Okay, I'm going to jump down here. Let's look at Ne. Listen closely. I'm not doing the second one. I'm jumping down the page here a little bit. Ne. Find Ne on your periodic table. And we're going to kind of start this one the same way. Once you find Ne, we can determine the atomic number. What is the atomic number of Ne? Brooklyn, I'm recording so you can go back and watch it because we're just about ready to wrap up here. We'll be done in just a few moments, so you can go back and watch it later. Still waiting for somebody to tell me the atomic number of Ne. 10. Jacob, yes. Thank you, buddy. Right on. Got it. Atomic number is 10. Once I know that the atomic number is 10, what other thing or things can I fill in? Once I know the atomic number is 10, what other thing or things can I fill in? Olivia says protons. I agree with Olivia. Is there anything else that I can fill in? Electrons, yes, guys, very good. Let me jump over here and fill in the electrons. 10. Well done. All right, now I'm just missing this spot right here. How do I get the mass number? How do I get it? Jacob, I'm looking for the mass number. Yes, it's 21. What two things did you put together to get 21, though? I think you just typed it in wrong. It is 21. What subatomic particles get added together to give us the mass? Neutrons and protons. There you go. That's right, Olivia. Neutrons and protons. Remember, the things in the middle, when we were looking at that simulation, it was the orange and gray balls, the ones in the middle, that always changed the mass. So we got to add protons and neutrons. Just like in the first example I did with you, you knew that you could subtract the protons from the mass number to get the neutrons. So it's that relationship. Protons plus neutrons equals mass. Okay? Protons plus neutrons equals mass. If you'll remember that, you can rearrange that equation anytime you need to solve for any one of those three things if it's missing. As long as you have two, you can always figure out the other one. Okay? All right. Well, that is my lesson for the day. couple of things that I want to talk about real quick before I turn you loose. Number one, I just want to remind you, I briefly mentioned to you guys yesterday, and probably your other teachers did too if you have other online classes, that the scheduling window is open. So remember, I put in the stream that document that should be very, very helpful in getting you scheduled. There's videos. You can click on some of those links and go to videos. There's other documents. There's all kinds of stuff in there. There's hyperlinks all over that document that will take you around and show you the things that you need to use to help you get scheduled for next year. Okay? And so remember that scheduling window closes on the 12th. So that'll be here before you know it. It's next week already. So make sure you're working on your schedule. Also, then the rest of this worksheet is due for tomorrow. So go ahead and just fill in on your own worksheet. You all should have an electronic copy of it. Make sure you fill this in and pay attention. Pay attention. Okay? Because, for example, when you're going through here, notice neon here and neon here. And yet I just filled in 21 there, but I put 20 down there. Why would I do that? What's going on? And is that okay? And so make sure you pay attention to that and make sure you think about each one of these that you're doing. Don't just get in a rut and start filling stuff in. You got to pay attention. Okay? Ms. Hall, you got anything else you need to add?
Yes. So some of you guys, I have sent an email to you in regards to ACT for next week. It is titled ACT Important Information in all caps. You'll want to read through that email because I'm going to give you some specific directions in there and tell you some things. Also is attached is your letter for the non-testing portion of the ACT. And you need that to go online to www.myact.org to complete. And your student code is also on that piece of paper. So let's see. Brooklyn, I sent you an email. Ashton, I sent you an email. Kobe, I sent you an email. Bruno, you have an email. Caleb Lane, you have an email. Emmy, you have an email. And Michael and Tierney, just to let you two know that you have an email coming. But I am waiting on one more detail before I send you guys yours. So just be sure that you are looking at your email and paying attention to that and getting that information off there before we start testing for next week. Let's see, I'm trying to think here. Google Classroom. I think we had several people in here that have not done the last test. Unit 2, Quiz 1, Saul, Michael Frazier, Tobias, Will Raymer, Ava, Landon. You guys do not have a test turned in and completed for Unit 2, Quiz 1. So you need to let us know when you're going to do that so that we can get it unlocked so that you can get that completed. All right. Other than that, I think I am good.
All right. Thank you, Ms. Hall. That's what I've got for you guys today too. So get this worksheet completed and turned in, and I will see you all back here tomorrow. So have a great rest of your day.